Hi TJML. Today we're going to be talking about recurrent neural networks, their variants, and different ways how we can apply them. So to start off, this lecture was written by Vinay, a recent TJML grad, and the PDF will be available on the website if you want to check it out later. Recurrent neural networks are very helpful when it comes to processing sequential data. That's why they're really great when it comes to tasks like handwriting recognition, NLP, image generation, and image captioning, and so on. They actually, surprisingly enough, aren't that new of a concept. They originated as Hopfield networks created by John Hopfield in 1982. Because the purpose of an RNN is to handle sequential data, it uses the previous states it outputs. In order to account for the sequential data, we can see that the RNN structure loops back into itself. The previous hidden state from the last input is passed into the function for the current state. Let's use the sentence "I like dogs" as an example. Here, the first word, I, is passed through the network and results in some sort of output like usual. Then, the previous hidden state that was computed for I is passed into the function to calculate the hidden state for like and so forth. This is modeled by the equation right here, where W and U are weight matrices. S is the current state, S sub t is the current state, S sub t minus 1 is the previous state, and X sub t is the input vector. The function that the two parameters are passed into is an activation function like ReLU or hyperbolic tan. The output for each input is given through the function, where V is a weight matrix and the function is another activation function for classification, like softmax. All weight matrices, well, all of the weight matrices here, W, U, and V, are the same for each layer because we pretty much perform the same operation at every step. Something I want to point out is that even though we can produce an output at each stage, we can also choose to only use the ones we want. This is pretty helpful in scenarios like sentiment analysis, where we want to model many inputs to one output scenario. Overall, backpropagation in an RNN is similar to that of a regular neural network, using the chain rule as it takes a step back into time. However, one issue that arises comes from the loss function. Normally, to calculate the loss, we would have to find it by propagating through the entire RNN and summing all of the errors for every single gradient step. As you could imagine, for a really long RNN, this can take a long time, which leads to our solution, truncated backpropagation through time. So instead of propagating and then backpropagating on the entire network, we can do so in chunks. So looking at this chunk, after calculating the loss of this chunk of the network that we're working with, we update the weights accordingly. Through this method, the model converges much faster. Even though regular RNNs are great and have a lot of uses, they're also susceptible to the vanishing gradient and the exploding gradient problem. This means that through backpropagation, earlier layers either face an exponentially small or exponentially large gradient. As a result, in sequences of data, at the current time t, the RNN is likely to forget relevant data from long before. That's why we turn towards the Lstm, long short-term memory, which is a variant of an RNN. So, like we just introduced, the Lstm aims to solve the problem of the RNN, allowing it to retain relevant data from long before. The four main parts that compose an Lstm are the cell state, C sub t, the input gate, I sub t, the forget gate, F sub t, and the output gate, O sub t. We can see how the Lstm, even by initial glance in this image, is much more complex than the RNN through these cells. Here, we can see that the cell state serves as the main flow across the cells. The gates modify the information that is passed through the cell state. If we take a look, The X denotes element-wise multiplication, which is different from matrix multiplication, as we're multiplying the same position in one vector to the same position in the next. And the plus denotes element-wise addition. The forget gate determines whether or not the information should be added to the cell state. This gate is a sigmoid layer that takes in h sub t minus 1 and x sub t. It does it by multiplying the forget gate output with the cell state. Therefore, if the forget gate has a value of 0, then it would essentially quote-unquote forget the information. And if it has values of 1, it would remember all of the information. Next, we'll consider the input gate. This passes the input from the h sub t minus 1 and x sub t values and combines it with the new candidate values, which is represented by the c with the squiggle up top sub t. Because the new candidate values, the squiggly c sub t, takes in the inputs and checks if there are any new values that could be generated. And due to it being a hyperbolic tan function, it outputs values from -1 to 1, allowing the layer to generate negative correlations to a value as well. All of these values are combined and put into the cell state, which passes them through using the equation c sub t equals f sub t times c sub t minus 1 plus I sub t plus the new candidate values. So in other words, it would be the cell state equals the forget state times the past cell state plus the input gate times the new candidate values. The last part of the LSTM is the output gate. Here, it's just another sigmoid layer, which is combined with the tanh, hyperbolic tan again, of the cell state to give the final value which it is passed into the next cell. All of these gates would be trained through backpropagation as they're just layers in a network. But because of the large number of layers, LSTMs can be computationally expensive, which is what we're going to be talking about and trying to solve next. Gated recurrent units, or GRUs, combine some gates together. For example, the forget and input gate become one update gate, along with the cell state and hidden state merging. There are a couple of other changes for efficiency. Now, because we have fewer layers to train, thanks to merging them, we'll have a faster model. GRUs are pretty new, especially compared to LSTMs, as we discovered GRUs in the last decade compared to LSTMs in the late 90s. With a basic understanding of RNNs, we can look at actual applications, including language modeling. Here, there are two primary ways we can model language, either character by character or word by word. For the first method, the character by character method, we would have a list of all characters that are available in our vocabulary. So if we were to use English as in our example, we would have 26 letter characters along with all 10 digits and any punctuation we might need. The word by word method is the same, but instead it's comprised of all of our vocabulary as opposed to all of their characters. We represent our data through one-hot encoding, meaning that our input vectors would be of size 1 times our vocabulary size. The reason that we choose to do it through one-hot encoding and have our vectors the way they are is because if we were to set each vector to be of size 1 by 1 and increment the value based on the content of our vocabulary, it would learn that certain pieces of data were closer than others. For example, if we had the vocabulary of a list A, B, C and set the vectors for each one respectively to be 0 to the A, 1 to the B, 2 to the C, our model would conclude that A and B are closer together than A and C, which is not something that makes sense in this context. The sequence-to-sequence, seek-to-seek model is used to map one sequence to another sequence. This can be done by using two RNNs, one as an encoder and the other as a decoder. The purpose of the encoder is to take in a sequence and map it to one output vector, and the decoder takes that one output vector and maps it to another sequence. This results in an encoder being a many-to-one structure, while the decoder is of a one-to-many structure. Seek-to-seek models are helpful for things like chatboxes, and language translation. And they learn to stop training with a token appended to the end of the text, like end of statement, which signifies that the translation is time to stop. So, autoencoders. The goal of an autoencoder is to compress a vast amount of information into one dense object without losing any information. The middle part of the autoencoder, right here, is the compressed version of the data. So if we were to code this model, everything is done the same as if making a standard model, but using the library keras, we would run model.fit x, x instead of model.fit x, y. This is so that the model can map the same value to itself while also compressing it inside the image, so right here. This is helpful in seek-to-seek models as the middle part of the autoencoder represents a universal part of the text. An example would be while translating between English and German, the RNN could encode the data into one vector with the information and pass that through a decoder to translate the original text. So from the past slide, we've learned that seek-to-seek is incredibly useful just with the translation example alone. However, we do have to entirely rely on the last token of the encoder to contain all of the information for the entire output sequence. Every part of the input sequence should play a different role for each part of the output sequence. Looking at the attention RNN here, we pass in a weighted combination of the input states into each RNN cells, which allow each output result to attend to different parts of the input sequence. This concept is known as attention. For each state of the decoder at a time step, S sub t, the sum of each weight is multiplied by its respective input hidden state is added. When we visualize the weight matrix, we can see what input words contribute to each output word in the matrix image, right here. In this visualization of a translation of a French sequence to an English sequence, the squares that are lighter, so we can see like across the diagonal approximately, show where the attention is activated. For example, we can see that the first box on the top left shows that La contributes to the output of destruction. The overarching trend shows that the model goes through the inputs in order, for the most part, when generating the output. However, we can see attention really working in examples when both the inputs La and Siri, here and here, contribute to the output term Syria, here. An important concept in attention is the idea of hard attention versus soft attention. Hard attention simply focuses on one fixed area of the input, whereas soft attention takes in the weighted distribution of where to look. This difference can be particularly seen in the image representing a bird flying over a body of water. On the top row, each image shows a direct location that is being each image shows a distribution of the regions that are being looked at, but in the bottom row, each image shows a direct location that is being looked at. Because hard attention makes it so it's not differentiable, different techniques have to be applied to work around that. Although attention seems to be quite helpful as the input sizes and output sizes increase, so do the number of values for attention needed to increases by a lot as well, making it potentially inefficient for long character by character models. A cool application of RNNs is filling in areas of an occluded image with 2D RNN. The two main techniques used were the row Lstm and the diagonal by Lstm. While we aren't going to be going to the row Lstm and diagonal by Lstm in detail, the general idea is that the row Lstm went by pixel horizontally, while the diagonal by Lstm went by pixel on the diagonals with a convolutional kernel size of 2. In the image on the slide, the left slide contains the input image with the occlusion, and on the right are the ground truth images. The images in between here are the generation by the network. So while the generations are imperfect, they generally do emulate the ground truth photo. So for example, something like this and this are pretty far off, but here and here are pretty similar if we ignore the floor. The deep, recurrent, attentive writer, draw, a mouthful, is a RNN used for image generation in a way that imitates the way humans create images. Looking at the model, it seems like an autoencoder. It's actually a different type of autoencoder than what we talked about a couple slides back. This network, in particular, uses a variational autoencoder, VAE. They're pretty much generative autoencoders. This encoder creates a latent vector that has a probability distribution, which the decoder samples to create the generated image. This ensures that different images can be generated through the same input image because the model learns the underlying distribution pattern. That's great, as we don't need to continuously need new images to create more. Here, we can use the RNN to sequentially make the generated image over time. If we look at the sequence of generated images at each time step, the model is drawing on the entire image and making small changes each time. In order to make the model move around as if it were actually drawing by hand, naturally working in one area to another, it'll use attention. In draw with attention, so this example with the red and black images of the digits, we can see that, simply put, the added attention gate informs the model where it should focus on, and it changes at each time step until the model is done creating its images. The image of the house numbers right here is just an example of how accurate or close to real draw can get. Personally, I can't really tell the difference between real house numbers and generated ones in this case. So to conclude, there are a lot of different types of RNNs and fields that they can be used in. Hopefully this lecture was a good first step in understanding them as a whole, and thank you all for sticking with me and listening to this lecture. As always, if you have any questions, feel free to put them in the chat or message me. And this lecture, the slides, and yeah, that should all be on the website by the time you're watching this video. So if you want to review any of this material, feel free to go on there, ask me, ask any of us. So